Hello and welcome to this first part where I'll show you how to use third medium contact in COMSOL. The first example we'll be looking at is the C-shape contact problem, which is the one you can find here on Wikipedia if you just look up third medium contact method. And more specifically, we have a C-shaped structure. It is clamped here on one edge, and then we enforce a displacement at another edge until this upper beam comes into contact with the lower beam. And in between these beams, we have a mesh, and this mesh contains the third medium in our case. And in order for this to work, we'll need to add a regularization. Today we'll use the HuHu regularization. I've also added a link for the HuHu-LuLu regularization, which is a later improvement of the HuHu. So essentially what this HuHu regularization does is that it takes the Hessian of U and does a triple contraction by itself. This way we add a penalization on all higher order deformations, and we add that directly to the strain energy density expression. And then we scale it by these terms. So we have a scaling constant, Kr, which we'll define soon. And then there's an indicator function, which we'll not treat explicitly today. And then we have this scaling term, the exponential of -5 times the Jacobian. And that essentially just increases the weight of the regularization as the material becomes compressed, such that highly compressed elements, they're more heavily regularized by the approach. Okay, let's delve into COMSOL. Just use the model building wizard, choose 2D. We deal with solid mechanics. So let us add this solid mechanics study, and we want to do a stationary analysis, and done. I am by no means an expert in COMSOL, so if you have any suggestions on how to do this better, then please write it in the comments. I only started using this software a few days ago. First, we want to define some global parameters. We'll need a bulk modulus. We'll let the value be 1 for this case, and then we need a shear modulus, choose 0.4. We need this regularization constant we just talked about. In this case, let's just choose 10 to the power of -5. And then we'll need a variable for the enforced displacement. Let's just say 1. Okay, now we've predefined some variables. Now let's go into definitions. And here we want to add a definition, so we say add variables. And now we want to add the HuHu regularization. And we'll just call that HHtest, because it's the weak form of this expression. And I've cheated a bit and prepared this beforehand. So I have the weak form of the HuHu regularization term here. And I've left this term in the description, and there's also the term for the HuHu-LuLu, and you have it in 2D and 3D. This explicitly is only the 2D version. Okay, then let's add it here. Boom. And now the HuHu term exists. Let's go into geometry, and now we need to build our problem. Let's say a rectangle. Width, let's say 2.05. And then let's add another rectangle of width 1.8, 1.8 this time, and we'll start it at the edge 0.2. And then we'll add another rectangle, and this will have the width also 1.8, but it will have the height 0.6. We'll start at x 0.2 and 0.2. They say build all objects. Just zoom so we can see them. And now we can actually see that the different rectangles here, they have some intersections, and now we get these C-shaped problems. So this will be solid soon, and this will be solid, and then this third medium, there's some void buffer region here. This you can find in the paper I showed earlier. It's also linked in the description. Okay, now let's go into our solid mechanics model. We want to be adding a hyperelastic material law, and we'll choose New Hookean, which is the default here. we want to define it in terms of the bulk and shear modulus. And first we want a user-defined bulk modulus. We say 1 times the bulk modulus we specified earlier, and similar for the shear modulus. And then the density, that's actually irrelevant in this case. Okay, now let's manually select the regions where this solid model is enforced. That is in these solid regions. I want to add another hyperelastic material, and this is going to be the third medium. So if we just select the regions, it's this and this. Once again, HuHu material model, we choose bulk modulus, bulk to define in terms of bulk and shear modulus, user-defined bulk modulus, say this. So now we choose the bulk modulus for this HuHu material to be 1 million times less than that of the solid. That means essentially the third medium is just an extremely soft HuHu material model. And we do similar for the shear modulus. And we say user defined. Perfect. Okay, now in this third medium region, we want to add the HuHu regularization. In order to do that, we need this equation view. If you don't have this equation view in your COMSOL, you can simply click the eye up here, and then you tick off this mark which says equation view, and then it should pop up. And when we enter this equation view, we can actually see the weak form expression for the HuHu material law that we just added in this region. So that's the HuHu material. If we just take this out and copy it into a notebook here, and you can see the full expression. And now the signs are defined such that it's negative. So instead of adding, we actually subtract the HuHu regularization. So that we do simply like this. So it's KR, the scaling constant we talked about before. That's the one we see in here. And then we have this other scaling constant, which depends on the current material volume, the Jacobian. That is this expression. And then it's defined by HHtest that we just defined earlier. So you just copy this, and now we insert it into our COMSOL model. Okay, now the HuHu regularization has been added. Next thing we want to do is add a fixed constraint. We need to define the boundary conditions. We'll fix this left boundary where it's fully clamped, and then we want to be adding points and then a prescribed displacement. We'll add a displacement at a point here instead of an area, which is more common for the C-shape problem. And we will prescribe it only in the y direction. It will be minus y disp, the variable we defined earlier. I want to go into mesh and want to say mesh size, custom, and let's just say 0.05. And now we want to add a mapped mesh. I say build all. Now you can see that the entire problem has been meshed. And now the element type we can actually find in here if we go under solid mechanics. So you go into discretization and you see it has already chosen the quadratic serendipity elements. Ideally, you'd also choose the integration method. You'd like to use Gauss-Lobato or something like Newton codes, something that has integration points at the nodes of the elements. But I text the COMSOL, and currently they don't support this, but they might support that in a future release. So that would further improve the model. Okay, now let's continue to study. But maybe before we do that, let's just save our model here. So this is, let's just call it C-shape 2. Okay, now it's solved. We have a stationary analysis. And here we want to go into study extensions. we say auxiliary sweep, and then we add a parameter sweep into sweep over, and that's going to be this enforced Y displacement. And we will increase it gradually by saying range from 0 in steps of 0.05 this time until 1. So now it gradually increases from 0 to 1 in 0.05 in 200 steps. Okay, now we should be ready. So if we hit compute, hopefully we'll get some results. Can follow the progress down here. Okay, and now we have the deformed structure. Let's just quickly change the view here. We want to add a mesh on top of this so that we can see the deformed mesh as well. And we want to deform this mesh, and scale factor, we want to scale it by a factor of 1. Plot, let's go under the surface. And instead of plotting the von Mises stress, let's just plot the bulk modulus in the material. And then color table. Or is that under the? That might be under the mesh. None. Okay, now we can actually see it. So now we can see the complete deformed structure. Let's just quickly add an animation. That way you can actually see how it deforms. I think the default animation should do the job. So now you can actually see how the C-shape deforms. Okay, that was it for the first tutorial. If you'd like to improve the third medium contact model, you can try to play around with the discretization and also the stiffness of the void, but also changing the regularization, and ideally also, at least in future releases, the integration method that you apply.